Hello and welcome. This is Mrs. Ramthan, and today we'll be talking a little bit about three-dimensional models of molecules and how that is related to molecular geometry. When we identify different types of molecules, the models we use can help us determine different things about them. So when we think about something like the molecular formula, that's really just giving the numbers of atoms in the compound. That model tells us what's in it, but not a whole lot about its actual physical structure. A structural formula gives a little bit more of an indication of that, looking at the types of bonds between the atoms. So in this type of model, you would see double or triple bonds represented, as well as the relative positioning of the atoms with each other. A ball and stick model is going to give the length of bonds between nuclei of atoms in the compound. So you're going to get a little bit more accuracy about the actual positioning and distance of the nuclei from each other. Sorry about that. And space filling models will give more of a volume kind of diagram to be able to see how the atoms take up space relative to the other atoms in the compound. So depending on what we want to discuss or show about the molecule, different types of models can be more effective than others. So here we see an example of each for methane, ammonia, water, and oxygen. So molecular and structural formulas, not real detailed. Here we see that the ball and stick models are showing again that distance between the nuclei, and the space filling models are kind of showing more of that atomic size relative to each other. So when we look at different types of carbon-based compounds, the space-filling models really become very helpful as we look at the shapes of the overall molecules. So the positioning of the bonds and how they interact with each other can give a lot of clues to their properties and their behaviors. Notice that we get to kind of compare some of these different elements relative to each other. So here we have chlorine attached to this 2-carbon chain on the end, and here we have bromine that's a little bit larger. So remember that as we think about our periodic trends, bromine is lower than chlorine on the periodic table, so that makes sense. And then different types of things attached to each one. So this is an amine group. And here we have an oxygen between these two carbons. And here we have an oxygen on the end. So all of those different positionings will affect the properties of the molecules and the shapes that they have. Here we get to see an example of superglue. So many of these carbon-based compounds, these organic compounds, can get very large and complex. Insulin, a biological molecule, obviously far larger than the superglue that we just watched. The shape is going to be very important because the shape determines its function. So insulin as a biological signal molecule has to have the right shape to fit into its receptor where it needs to send its message. Now, when we look at models, some of the things that we're looking for can give us some hints about the bonds themselves. So one thing we can look at, especially in a ball and stick model, would be bond angle. So the angle is formed by two bonds to a center atom. So if this is our center atom, we could measure the bond angle from here to here. That's going to help give us something, some information about the shape that it has. The bond length, the average distance between nuclei, can be determined, and those are represented here with the ball and stick model as well. And remember that bonds are pretty flexible, especially single bonds. So when we're looking at the physical spacing of these atoms, remember that electrons are always moving and the bonds have some flexibility due to that. Now, when we look at the types of models that show these traits, think about the pictures that we have here. The ball and stick models will best show these properties. Now, when we take a look at this, what I'd like you to do is determine the molecular formula or, blanking out, the chemical formula for fluoxetine, and then calculate its molecular mass and molar mass. We're not going to worry about molar mass so much right now, but molecular mass is measured in AMU, which you can find on the periodic table. So if you know the molecular formula, you should be able to determine the mass of one of those molecules. And notice here, a red represents an oxygen, the grays are the carbons, blue is nitrogen, ivory ones like here are the hydrogens, right here, and then these kind of yellow-green ones are the fluorines. So hopefully, if you paused and took a moment to do that, you arrived at C17, H18, F3, N, and O. So notice there's only one N and one O. So my molecular mass, let me go back and we'll add those in. Give me one moment. All right, we got it. So you should have arrived at 309 AMU. We calculate that by adding together the masses of the individual elements within the formula. So we would have added together each carbon has a mass of 12.01. Each hydrogen has a mass of 1.01. Fluorine, I believe, is 19.00. Don't know why I did that. Nitrogen is 14.01. And oxygen is 16. So we would have multiplied this times 17, this times 18, 3 times the 19, plus the 14.01 and 16. Molar mass is going to be the same value, but a different unit. We will be getting to that very soon. So how does this connect to the shapes of the molecules? Well, we learned in the POGIL that the VSEPR theory helps to explain the way that the electron domains behave relative to the center atom. So whether they are non-bonding electron domains, like we see here in these lone pairs of electrons, or bonding domains, like we see here in the shared pair between the oxygen and the hydrogen, they will spread out as far as possible in three-dimensional space. So the number of non-bonding and bonding electron domains together is going to help us determine what shape a molecule will have. So here we see a table that's broken up by the number of domains, and they use a little bit different language. So charge clouds would be the same as total domains. Lone pairs would be the same as non-bonding. And number of bonds would be the same as bonding regions. Now you will have access to a table or a handout that shows the same kind of information when you are doing work like this. So you will want to make sure that you become familiar with how to use it. So here we see that if I have 2 bonds and no lone pairs of electrons, that gives me a total of 2 charge clouds or electron domains. The geometry or shape of this molecule will be linear because they will spread out on opposite ends of each other. An example of this would be CO2. Notice that we are not seeing all of the valence electrons on the end atoms. We're really just emphasizing the valence electrons on the center. Those are the ones that determine the shape. Here, when we have 3 charge clouds, there's 2 different ways to achieve that. I could have 3 bonds and no lone pairs, or I could have 2 bonds and 1 lone pair. Depending on what I have, I will have a different specific shape, because when there's just a lone pair of electrons, they're affecting the shape, but there isn't an actual atom there. So here we see, for example, the shape is bent because it makes this kind of V shape because this pair of electrons is pushing down on those bonds. With 3 bonds, it's considered trigonal planars because there's 3 bonds and it's all in one plane. It would be a flat molecule. The more charge clouds we have, the more complex my options are because there's more variety of ways I can combine lone pairs and bonding regions. So this chart distinguishes between those for kind of our typical octet-based molecules. Notice again that we have a bent shape here as well. One of the biggest things that's going to differ between these two is going to be the bond angle. Notice that when there are more domains, the bond angle will be different because they will spread out differently. There's more that's going to have to be kind of spaced within that three-dimensional positioning. So the bond angle will be smaller in the 4 charge cloud than the 3. As we start getting into 5 charge clouds, these are going to be our extended octets or rule breakers. So keep in mind that many of the standard octet ones will fit with one of the shapes that we had on the last page. What I would like you to do at this time is to kind of pause the video to be able to record these different shapes that you see so that you're able to record all of those examples in your table. I would highly recommend that you draw the shape the way it is meant to be drawn by the three-dimensional shape here to help you understand what the shape is. So when you give the example, like let's say we did this one and we just wrote PCl5, you also want to either draw this picture or draw the ball and stick model so that you can understand what that shape looks like. At this point, you will then have kind of this reference sheet that we will be using as we move into our molecular geometry lab. You will work from the Lewis structures that you've drawn in the past to determine the molecular geometry and then use the kit parts or the online PhET simulation to model those shapes and to identify the correct shape that they should have.